The first law of thermodynamics is based on the law of conservation of energy, which says that energy is neither created nor destroyed, it can only be transformed. Now we can represent this saying by the following formula. So our delta E is the change in energy, Q is the heat, and W is the work done to the system. Now, in order to solve problems on the first law of thermodynamics, we're going to need to be familiar with two different situations. So we can either have a closed system or an open system. So let's take a look at their corresponding formulas. So for a closed system, we can see our previously mentioned formula over here and its transformed version. So we have our change in internal energy plus our change in kinetic energy plus our change in potential energy, which are all different types of energies going back to our delta E. They're all equal to the heat minus the work from state 1 to 2. For an open system, the formula might look a little bit different, but it's still based on the same principle. So we have the first law, but under the instantaneous time rate form. So we have dE over dt, the energy over a time period, is equal to the heat minus the work. So in the transformed version, we can see the summation of the mass flow rates that are going in the system, and then minus the summation of the mass flow rates that are going out of the system. And instead of having internal energies, we have enthalpies.
In order to have a better understanding of the first law of thermodynamics, here is an example problem taken from the course problem pack, and this is question number 5.16. And it says, a compressor is used to compress helium gas from 120 kilopascal and 300 Kelvin to 750 kilopascal and 450 Kelvin. A heat loss of 18 kilojoules per kilogram is found during the compression process. Neglecting kinetic energy changes, compute the power input required to maintain a mass flow rate of 88 kilograms per minute. Before we begin solving the problem, it is a good idea to first write down the given variables. So, in the problem, P1, T1 are given us 120 kilopascal and 300 Kelvin, while P2, T2 are given us 750 kilopascal and 450 Kelvin. Next, small q, or the specific heat, is given as 18 kilograms per kilojoules per kilogram. However, this is negative because there is a heat loss in the surroundings. And the mass flow rate is given as 88 kilograms per minute. However, we want in seconds, so we just need to divide 88 by 60, giving us 1.46 kilograms per second. And we could also find the big Q, which is the heat, by multiplying the mass flow rate with the specific heat, and giving us negative 26.4 kilowatts. And this is kilowatts because when you do kilojoules over kilogram times kilogram per second, the kilogram will cancel out, leaving us with kilojoules over seconds, and that's equivalent to kilowatts. And as the problem states, the kinetic energy is neglected, so the KE will be 0. And then the problem is asking us to find the power input, which is a W. And since this is an open system, this is the equation that we need to use to solve the problem. And also, it is a steady flow process, so dE over dt is going to be 0.
So, as we know, d over dt will be equal to 0. Q is already calculated. We are looking for the work. We can neglect the kinetic energy and the potential energy, so that's why they are equal to 0. So we are left with this equation right here. We can also substitute H1 minus H2 by Cp times T1 minus T2. Cp is found in the tables, and T1 and T2 are given in the problem. So we are left with minus 26.4 kilowatts plus 1.46 kilogram per second, which is a mass, times Cp, which is 5.1926 kilojoules per kilogram times Kelvin, times the temperature, which is 300 Kelvin minus 450 Kelvin. So our answer is a negative work of 1168.78 kilowatts, which means that we need to input this amount of work.